Hi, this is Jose Luis here, and welcome to another video on this series, Introduction to Parametric Modeling. In this exercise, I would like to show you the super fundamentals of how to create a slicer that you could use for 3D printing operations and how to compile an output of that slicer that could look like G-code and that could be used for 3D printing that object. So in this exercise, I will bring in some random mesh, like for example, the Stanford bunny, and then I will perform a few operations to generate a layered sections and layered contours. And of course, everything is going to be parametric, so we can calculate how many layers we want, etc., etc. And then we will do very simple textual operations to generate something that looks like G-code so that this could potentially be plugged into a 3D printer, press go, and then get the bunny printed. Now, full disclaimer, this is not going to be a working slider. This is not going to be a slicer. It's not going to be a working G-code compiler because making this actually that way that it works and in a way that it works for all kinds of geometry, and it does infill and it does overhangs and it does support material, and all of that is actually way more involved than we're going to see here. I just want to show the basic process of taking geometry, slicing it, and then turning that information into a text representation. But if you actually want to do this manually, there's like many more things that you need to take into consideration than just what I have shown you, what I will be showing you here today. Okay. So, all right. So I think with that, I would like to get started. Let's talk about how we're going to do this. The basic idea or the basic functionality behind any slicer is actually quite simple and quite straightforward. It is making it work consistently, right, and across all possible geometries, all possible forms, and in a way that doesn't break and doesn't sag the 3D print. That's what's actually really difficult. But at the core, the level, foundational level, is a very simple operation. Let's imagine we have any random geometry, right? The first thing we need to do is we need to turn it into a mesh. And this is very important because no slicer that I know of in the market, in the world, works with NURBS geometry. Internally, they always end up translating it into meshes. And this is because since the since the process of slicing involves creating a set of planes that are spaced a particular distance between them, then intersecting the object with that plane and then subdividing each one of those contours into individual points, it turns out that the fact that that geometry is made up of triangles actually speeds up and makes the process extremely easy, because cutting through triangles with a plane is a really basic operation. Doing it millions of times is what a computer can do very well. But at a core level, cutting a triangle with a plane is a super simple operation to do. So doing it many times is very easy to do for a computer. But also discretizing the contour, discretizing a contour that is made out of polygons, because when you cut a triangle you get straight line segments, is also a very simple thing to do, and is very convenient for a 3D printer in particular, because a 3D printer really can only do straight line segments. It cannot move in a real perfect smooth curve. So when we want to do curves with a 3D print, what we do is like tons and tons of tiny straight line segments. All right. So that's why meshes are the default de facto standard for 3D printing. Now, and then the last process is, once we have all these contours and all this subdivision, and for this exercise, we're not going to bother about infill material, we're not going to bother about overhangs and support material. All of that is the stuff that is actually difficult and is still undergoing a lot of research these days. We're not going to care about that. And what we're going to care is about the last process, which is taking all of this information and turning it into some kind of textual representation that a machine can read. In our case, we're going to be inspired by G-code, which is also the standard in 3D printers. And we're going to write a super oversimplified version of G-code, which is not going to be functional, all right? But it's going to be a starting point if you actually wanted to implement a real slicer with a real G-code compiler, okay? But this is going to be more of an exercise to seeing how the whole process works, and also a tiny bit of how can we create text in a procedural parametric way. So all of this is actually going to be super easy. It's going to be like 10 components or 12 components tops, okay? Let's take a look at how that would be. Okay, back in Grasshopper, I have loaded this mesh model, which is the Stanford Bunny. And for those of you who may not know, the Stanford Bunny is actually this one particular model that has been used in computer graphics and 3D modeling for a long time, since the 70s, I believe. It has a lot of history to it as well. If you can actually Google and nerd out a little bit about the Stanford Bunny. But long story short, it's a model that is very often used for testing things that relate to meshes. And if you read technical papers, for example, on computer graphics, you will see this particular bunny in many of the examples of people working with meshes, people working with 3D scans, people making operations, segmentations of meshes, etc. It's like the Utah teapot. It has a whole history behind it. Anyway, I took this model that I oversimplified and I downloaded the mesh count, the face count, to like 1,000 or something. So it's a simplified version of that model. And then I'm going to bring this into Grasshopper. And now in Grasshopper, I'm also going to add a parameter, which is going to be, for example, the layer height. Typically, what we do is we control the height between the layers, and that depends on the diameter of the filament we're using, the resolution of our printer. I don't know. This is some of the parameters that we set when we have a real slicer. And then the way we're going to start is, as we discussed on the diagram, the first thing I'm going to do, I'm going to create some kind of vertical arrangement of planes, and that I'm going to use for slicing this bunny. So that can be, for example, a good way to go about that is taking the bounding box of the bunny and then finding the base point and then creating a set of planes, a set of layers above in the C direction. So what I'm going to do is I'm going to go to boxes, bounding box, and I'm going to create the bounding box of this mesh. So that's going to be one thing. And then I'm going to decompose the mesh into a wire frame. And then I know that the A and the E, because I did it in the previous exercise, not because I remember, but I know that the A and the E are the 2 points that are here on the bottom left side of the box, so that I can create a vertical line that kind of represents the height of the element. And then what I would like to do is I would like to populate this with XY planes at a control distance. So in many exercises in this series, we have subdivided curves into equal length segments. However, in this case, this way of dividing curves will not work, because what we want to control is the actual distance between the planes, not the fact that there has to be 10 or 15 or however many planes. So that's why I'm going to choose this other division method, divide a curve into segments with a preset length, the length being the layer height. And therefore, what this will do is that it will divide that curve into a bunch of and you can see that if the distance doesn't really fit exactly to the length of the curve, then that part will basically be lost, which I'm pretty cool with that. So that layer will just not be printed because it's not enough. There's not enough resolution for whatever reason, okay? So I have all these points here now, and I can create XY planes on top of this. And these planes are going to be the slicing planes for the bunny. So let me hide this bunny, and then let me make sure that I can see the bunny. And then very simply, I'm going to go to the intersections tab, and I'm going to go to mathematical, and I'm going to find a way to intersect the mesh with all these planes that I have created, the planes that are going to do the slicing. This component is going to be this one here, solve the intersection between events for a mesh and for a plane. Okay? So the mesh is going to be the one that I have as an input here, and then the planes are going to be all these planes. And you can see that the operation is pretty lightweight because I only have a few planes, but if I double the amount of planes, so for example 0.15, now like the operation is a bit more expensive, and but you can see that how very nicely I have all my sections for the bunny. And if I turn this off, you can see all the cuts and all the contours that I would be using for 3D printing this bunny, which is kind of nice, correct? So I'm going to crank this up to 0.1, or actually no, I'm just going to keep it a little low because something that I would like to show you as well is the result of this operation. And if I plug a panel here and I look at the contours, I can see something very interesting. So I can see that the outcome of this component is giving me a data tree structure, which is very nice, where each branch represents all the intersection events for each one of the planes. And we can see that the very first one, because it's coming from this bounding box, is giving me no intersections, which would be a terrible thing for 3D printing, because in 3D printing we actually really need a base to stick to the stick to the base of the printer. So that's something that we should definitely improve at some point. But you can see how we have an empty branch here. Then most of the branches of the bunny are single contours with one polyline curve. However, as soon as we get to the head and to the ears, we start getting branches that have 3 polylines, 2 polylines, and 1 polyline. So you can see, for example, that this one here has this one, and this polyline. These ears, they have 2 polylines, and this one has just 1. And if I change the number of cuts, we're basically going into a similar situation, right? Where now I have here 2, 1, 1, 2, 1, 2, 3, etc., etc. If I were to represent that tree with the parameter viewer here inside of utils, I can plug this in here. And if I double click, you can see that I would be getting, actually it's a little difficult to see here. Let me reduce the count of limit of this. So you can see how, oh yeah, no, yes. So I can see how this is, yes. So I will show that back in a second. Okay, I will get back to that in a second. So this idea, the idea that we have a tree and that has like different elements per tree. So some of the lists have more elements, some of the lists have fewer elements or even no elements whatsoever. This is not a very common situation in Grasshopper, but it happens sometimes, especially when we're working with geometry that doesn't have clear logics internally. Like for example, this bunny here. So this kind of data tree is typically referred to as a sparse data tree. I think actually sparse refers to more specifically when a data tree has a lot of empty elements, but the idea that a data tree is not homogeneous, so not all the branches have all the same elements, that can be referred to as a sparse data tree as well. So that will be super, super interesting. Now, what is the next thing we need to do? We need to find for each one of the polyline curves, we need to find all the points that we will need to make the 3D printer head go to. We cannot give polylines to a 3D printer head. We need to give them X, Y, Z coordinates of each one of the points that it needs to go through. So how are we going to do that? We need to extract from these polylines each one of the vertices of the polyline. How can we do that? That's going to be actually super easy. We're going to go to curves. We're going to go to utilities, and there's this one component here that is called explode. Explode takes a curve and it divides it into smaller segments, the segments that make up that curve. For polyline, that is going to be a ton of straight line segments. And for example, you can see that I have all these, for each branch, I have all these straight line segments, correct? But for vertices, it's going to be the exact same thing. I'm also going to have a ton of, this component is also giving me vertices, and I'm also getting a ton of vertices for each one of these curves. Now, what's interesting is that this tree now looks kind of weird, because it looks kind of weird because I had all the original tree, the big trunk, but now this branch has branched in 3 ways. This had branched in 2 branches. This had branched in another sub branch. Why is that? That is because the tree that I had before, if you remember, had some branches with 3 curves or 2 curves. So now what has happened here is that Grasshopper has taken, for each polyline, it has created a new sub branch. So therefore, if you look at this, now we have the new level is 0, 0, 0, 0, 0, 0, 0, except for branch 11, which is the one that had the 3 polylines. And for this one, it has created 3 sub branches, one for each one of the polylines. For branch 12, it also created 2 sub branches because we had 2 polylines on branch 12. And then for 13, it only created the 0. So you can see how the levels in data structures actually make a lot of sense based on the operations that we are coming from. All right, which is, I think it's a very smart design, actually. It's a very smart thinking. So we have all these points. What do we need to do next? Now we need to do some kind of G-code compiler. How is that going to work? So what is G-code in a nutshell? Well, we're not going to get into the weeds of that because it's its own thing. Actually, writing G-code is not very complicated. It just takes a little bit of time to learn the language and to learn all the codes. But in a nutshell, G-code programs are programs that have a textual representation for how to tell the machine to turn certain things on and off, and especially how to move in 3D space and where to deposit material or not. It's very specifically designed for 3D printers, but it's also used in other environments, such as, for example, laser cutting, and such as, for example, routing, so like milling, for example. The long story short is that a typical G-code program is composed of a lot of lines that look like this. They start with some kind of instruction code. So for example, G1 is to move in an absolute, I think it's moving to an absolute location. And then some kind of parameters that are a letter representing what the parameter is, and a number representing what the value for that parameter is. So for example, G1 and all of this indicates that we want to move in absolute coordinates to the coordinate X and Y with these numbers. And for 3D printing, F means the speed at which we're moving, and E means how much material we're going to deposit in this movement. Okay? But if you want to learn more, there's like the Wikipedia page. It explains like where G-code comes from and explains the overall families of codes and the specifics of each one of them. I would also like to let you know that G-code has specific flavors and different machines take G-code in different ways. So depending on which machine you're targeting, you should take a look at how they interpret G-code. But I have consistently found that the RepRap guide to G-code is actually pretty good and pretty exhaustive. So I would recommend that you check this one out if you want to. So for example, G1 is to move, and it tells you which printers support it and which parameters and it comes with a sample. It's a really, really good guide, okay? But again, my intention in this exercise is not to write a full-fledged functional G-code compiler. It's just to give you a sense that what we're going to do is we're going to translate from geometry that we have into a program that is going to have a bunch of these textual lines with the information. So if that's what we need, then basically, if you remember, in Rhino, what we had was this situation where we have a tree that has a lot of vertices, so each one of the X and Y and Z locations of where the bunny is in 3D space and the journey that it should follow. And what we need to do is we need to turn each one of the coordinates of these points into something that looks like this, that looks like a G-code instruction. So the G1 to move, and then the X, Y, Z coordinates with their numbers. So the only thing that we need to do is we need to translate what now for us is points into a list of text representing the G-code instruction. So this is going to involve a little bit of text creation and text manipulation, which we also haven't seen in this series, but it's really, really easy to do. Text can be done where here under sets, there is a category called text, which allows you to do text operations. So join text, create text, split text, do regular expressions, like a lot of different things. And for us, it's going to be super simple. The only thing that we need to do is we need to concatenate in one single line of text. We need to concatenate all the text that we need, so the G1, the X, the Y, the Z, whatever, with the values representing those points. So I'm going to drop here a concatenate, okay? And then the first part of my G-code string is going to be, for each point, is going to be the G1 instruction. So the first thing that I'm going to concatenate is going to be G1. And then I'm also, because I will need to add, I'm going to skip the speed. I'm not going to care about that for right now. I'm going to do the X coordinate. So I'm going to write G1, space, and then the X. I'm going to write an X. And this is going to be hard-coded, so I'm just going to leave that there. Then the second parameter that I'm going to join to is going to be the X coordinate of each one of these points. For that, I will need to deconstruct the point and get the X coordinate and plug it in here. Now, I need to concatenate more stuff in here. So you can see that this particular component, I can zoom in and it gives me the option to add more inputs. So I can click here to add another input, and then I'm just going to copy and paste this and say, all right, after the number, what I need, after I get the number, I need a white space and I need the letter Y. So I'm going to do here a white space and the letter Y. I'm going to plug that in here. I'm going to add another input, and then here I'm going to plug the value of Y. Then next thing I'm going to do is I'm going to add another input that is going to be Z, the white space, Z, and then the last thing that I'm going to plug in is going to be the value of Z. Correct? And once I have that, then you can see that if I plug in a panel, we are going to have all this stuff here, okay? And you can see that the code is starting to look a little bit more like G-code. Obviously, we need the feed, we need the extrusion speed, we need a lot of commands for like turning the printer on, turning the printer off, setting the temperature of the bed, of the head, waiting. There's a lot of additional stuff that goes into actually writing G-code. But this is the basics, just taking numbers and turning them into sequences of text with a particular formatting. And actually, if this were millimeters, like I'm not sure that we would need 6 decimals for millimeters. So I think with 3 or even 2 decimals, we would probably be pretty good to go. So yeah. Now, a couple things. When we create text for a G-code program, for example, when we create a G-code program, we don't really need all the branching instructions, correct? So I would need to eventually, at some point, flatten all this information whenever I was ready to send this to the printer. However, in this case, it would be super interesting to maintain the branch instructions, because at some point we also need, as part of the program, to make operations such as at the beginning of a contour, we need to approach the contour from above, and then we need to lower down. So at the beginning of the contour, we will need to move the pen down, turn extrusion, and then start extruding all the way in. Also, something that I have not done, for example, is that at the end of the polyline, maybe if the polyline starts here and ends here, we may actually not print this segment here. So a very smart thing to do typically is to duplicate the last point twice, so that it's at the beginning and at the end. So the 3D printer goes like this, but we make sure that the ends at the same point. And then after that, I would like to add here like a tiny movement where the printer, the head moves up and then finds the next target and then goes down. So all those things will be super easy to do if I have everything structured with branches like I do have here. And then at the end of the day, at some point, so that would be for like a real G-code compiler. And last but not least, you can see that here I have an empty line that looks like an error because it doesn't have any numerical data. That is happening because remember that I have an empty branch here that has no cuts, no sectioning, and that is leading to a branch that has no numbers for no points, and therefore we have this empty line here. So a way to do that and to avoid that is to clean up the tree before we start operating with everything. We can clean trees here by going to the clean tree operation, right? And then take the tree that we want to operate, which is going to be here, and make sure that do we want to remove the null items? Yes. Do we want to remove invalid items? Yes. Do we want to remove empty branches? That's actually what I want to do. And you can see that by default is turned false. So I can right click here and set Boolean to true. And therefore now this tree has been cleaned and stripped down of empty branches. And if I plug that in here, sorry, not in there. If I plug that in here, you can see that now I don't have that trailing empty branch being annoying anymore. Okay. And now I have my tiny program that is like more than 1,000 lines of code for G-code printing. You know that G-code can be like thousands, if not millions of lines of code, very typically for complex prints, okay? But you can see that we kind of wrote a G-code compiler with 10 components, which is kind of nice. Again, this would not really be functional. There's so many more things we need to do to ensure that this would be printable, but conceptually, this is how it would be done. Okay, so with that, I think this is where I want to leave this exercise. If you thought this was useful, then maybe like this video or maybe even subscribe to the channel. Otherwise, I will see you on the next videos down the road on this series. Okay, thank you very much. Bye bye.